Today we're going to look at inverse functions. Now an inverse function is the original function reflected across the line y equals x. Now you might remember this from when we did matrices, and you might remember the transformation matrix to do this was the opposite of what we'd normally use and looked like that. And this had the effect of reflecting anything across the line y equals x. Up here you can see we have a point 2, 1. The orange dotted line is the line y equals x on 45 degrees, and the orange point is 1, 2. Now you can see that it's the opposite of the point 2, 1, and what I mean by opposite is that the x value and the y value is swapped places. And you can also see that it's at the position of the orange point is at right angles to the purple point across the orange line y equals x. This orange point here is the inverse of the purple point. Using the transformation matrix, I'll show you how that would have worked. So what I'll do is I'll write up the calculation as we would have done it using the original point, which was 2, 1. Now we know that it multiplies rows by columns, so therefore this one would be 0 times 2 plus 1 times 1, which would mean that 0 times 2 is 0 and 1 times 1 is 1. That would go in the top position. The bottom position would be 1 times 2 and 0 plus 1. Sorry, 0 times plus 0 times 1, which would be the bottom position. So 1 times 2 is 2. And you can see there that from my original point 2, 1, they've just swapped spots and become 1, 2. So this means the orange point up here is the inverse of the purple point, or the original one. Now I'm going to show you a few examples dealing with functions, not particularly points, and there are a few important pieces of information that you must remember when doing this. So the first one is that because the x and y values swap, as you saw in the matrix example, the domain and range also swap across the original to the inverse. And it's generally written like this: the domain of f equals the range, and the notation for the inverse is f to the power of -1. And this means that the other way is also true. The range of f is equal to the domain of the inverse. Now, it's important to remember that notation, f to the -1, because when you start to see questions dealing with this, they won't actually say in words, find the inverse most of the time. They'll just use this notation and expect you to remember it. The other important piece of information is when we can find an inverse function, and it's using the information we learned in the previous set. It's if f is a 1 to 1, then an inverse is possible. If it's not a 1 to 1, we can't find the inverse. And sorry about having to resize there. Alright, but you must remember that if the original function is a 1 to 1, then the inverse is possible. If it's not a 1 to 1, you cannot find the inverse. Now in this question, it's asked us to find the inverse function given by f to the power of -1 of the function given, 2x minus 3, as well as sketch the graph of the original, y equals f of x. This is a way of writing y equals f of x is the same as the function. And sketch the graph of the inverse, y equals the f to the power of -1 of x, on the one set of axes, which means we're going to see both graphs on one axis. To do this, we're going to need to use the information we learned in the previous slide and basically just swap the x and y values, which I'm going to write. I'm going to start by rewriting the original function using x and y instead of f of x, because it makes it simpler. This is the original function, y equals 2x minus 3. Now I'm just going to manually swap the x and y like this. As you can see, this is not the way we normally write a function. The way we normally write a function is for it to be y equals. So what I have to do now is to resolve this to get y by itself. So my first step is going to be move the -3 to the other side, equals 2y, then divide by 2. I'm going to end up with x plus 3 all over 2 equals y. So now this rule is equal to, or is the inverse. So I can write it up here, and I'm going to write it broken up the fractions, just because that's the way I like to do it. Half x plus 3 over 2, which is the same as what we found down here. Now, the question has also asked us to sketch the graphs of both the original and the inverse on one set of axes. I'm going to do a quick sketch and then I'll import a Desmos picture to show you, but you can clearly see that here, if the axes are going to be there, we're going to have half x plus 3 on 2, which is going to look something like this. That was the inverse, and the original was 2x minus 3. So it's going to look something like a bit of a steeper gradient. It's going to look something like that. You can see here that there is a bit of symmetry happening. The inverse, the top one, is looking like it's been flipped to become this one here. And I haven't drawn it very well, but you can see that these two triangles look like they're going to be roughly the same size, and there's space in here. The Desmos picture will actually show it a bit clearer. So here's the Desmos picture, and the red line is the original one. You can see it goes through the y-axis at minus 3, and it sits up here at about 3 on 2. Now the blue one is the inverse, and you can see it goes through the x-axis at minus 3. So this y-intercept has flipped to become the x-intercept, which is what happens across the inverse. Also note that both the red and the blue line intersect each other on the dotted line of line y equals x. Now this is a really important piece of information to remember. So there we have it. These two, red and blue, are the original and the inverse. We've talked about how to solve for the inverse, which is that you just swap the x and y in each, put them in each other's place, and resolve to get y equals. And then you can sketch both on the same set of axes, and you'll notice that one of them just looks like it's been reflected across the line y equals x to become the other one. For this example, we're going to look at a function that has a domain specified and see how that is affected by the inverse, or the inverse is affected by having a specified domain. So this one here says to find the inverse, and notice that it's given, instead of f of x, it's g of x, so the inverse is also g to the power of -1, using the same notation as the original function. It asks us to find the inverse function, g to the power of -1, of this function, remembering that it has a specified domain, and state the domain and range of the inverse, which we will find. Using the same steps as we learnt last time, I've first written the original function using y instead of g of x. Then I've swapped the x and y variables and resolved for y across these steps. My last one is to reuse the notation given, which is g to the power of -1 of x equals x plus 3 over 2, which is what I found up here in the previous step. This is now the formula for my inverse function, and that's what I'm going to graph. Now I have to go back to the original question and look at how the domain is affected. Now you might remember that when the x and y values swap for the inverse, also the domain and range swap. So the domain of the original, from 2 to 6, is going to become the range of the inverse. To find the domain of the inverse, I'm going to need to find the range of the original. I'm going to do that by substituting the endpoints into the original function. So up here we're looking at the endpoints. I've substituted x equals 2 in place of x into the original function, which becomes 4 minus 3, which becomes 1. Therefore the y value when x equals 2 is 1. I've also substituted the other endpoint, 6, in place of x into the same function and got the other endpoint, which is 9. Therefore, this means that the range of g goes from 1 to 9. Now the reason I use the included brackets is because in the original domain 2 is included, so if the x value is included, it also means the corresponding y value is included, and same at the other end. 6 is included, therefore 9 is included. Now we've been given the range, we've been given the domain of g, and we've just calculated the range of g, which means that we can just rename those two, and they will give us, or they are the same as, the range and domain of the inverse. We remember that they just swap spots, so I would write it like this. The domain of g minus 1 is 1, 9, which you'll notice was the range of the original, and the range of g minus 1 is 2, 6, which you'll remember is the domain of the original. So this is how we can apply our knowledge of inverses and domain and ranges to each other and see how they affect each other. Just to show you a bit more clearly, I've got the graphs, the two graphs. Now the original one was, the domain is the black one because the domain goes from 2 to 6, and you can clearly see here that the blue one, it looks like it's a reflection, and which it should be, and the range starts at 2 and goes up to 6. So you can clearly see that the domain of the original has become the range of the inverse. And I'll show you another picture which looks complicated, but if you take the time to study it, you'll see that these two things have changed spots. Now, the dotted lines on here are the domains and ranges. So the black line, the domain and range are in the green dotted line. So the black line, you can see that its corner or its start point is here, and it goes all the way up to this one. So its domain goes from 2 to 6, and its range goes from 1 up to 9, which we calculated. Now the blue line is domain and range is given by the purple dotted lines, and you can see there that it starts from 2 and goes up to 6. That's the range, and it starts at 1 and goes across to 9, which is the domain. So you can clearly see that the domain and range have just swapped spots from the original to the inverse. Now in this question, it's a similar sort of question except dealing with a quadratic. You can see by here it's in turning point form, x minus 1 squared plus 4. It's got a specified domain. It goes from 1 to infinity, which straight away you should be able to picture. It's not going to have a full turn. It's going to have a portion of it because it's been limited. Now, the first step is to calculate the inverse, which I will do the way I showed you in the previous two examples by swapping the x and y and resolving for y. So here you have the steps. I've written down the equation original form. As before, instead of using f of x, I've used y. I've manually swapped the x and y, and then I have resolved one step at a time to find y by itself. Remember that when you take the square root of both sides, you have to do plus or minus to cater for both solutions. Now this gives us the inverse, which I shall rewrite in the notation given, which is f to the power of minus 1 equals plus or minus x minus 4 plus 1. Also remember that the plus 1, because it came over after the square root, it sits outside the square root sign. Now to write the inverse in mapping notation, which I want to do, I need to know its domain. I have only been given the domain of the original, which means I need to find the range of the original to work out what the domain of the inverse is going to be. To do that, I'm going to graph the original function, which you'll see here on the right hand side. Now you can see that it starts at 1, 4. Now we know that the range of the original becomes the domain of the inverse. So for this one, the smallest y value is 4. That means that the inverse's smallest x value is going to be 4. So therefore, if I use that information, I can say that the inverse function, its domain goes from 4 all the way to infinity. And I will show you that by graphing both and inserting it for you here. I've put on both the function and the inverse. I've also put on the dotted line y equals x. So you can see here that the purple line starts at 4, 1, whereas the original line started at 1, 4. So its start point, its two coordinates have been swapped spots, and the domain of the purple one starts at 4 and goes all the way into infinity, which is a direct reflection of the orange one, which started at 1 and went all the way to infinity along the x-axis. I hope that those examples made sense. Please remember to use them in conjunction with your notes book, and feel free to stop and start them at any point and re-listen to all those things that I've talked about. Do keep in mind that we're wanting to start using all this mapping notation and the symbols and things like that, just like I've done here with the brackets, with the inverse usage here for f to the power of -1. rather than saying or using the y equals. We want to get in the habit of using our function notation with its domain and be familiar with reading mapping notation especially.